But okay, so I sort of rearranged with respect to last time, because last time we saw that actually for the example of PSL2Z, somehow we need to know already some facts about, in general, about the Dirichlet polygon. Oops. So yeah, so let's just show that the Dirichlet polygon, I mean, we're going to start showing with that the Dirichlet polygon is indeed locally finite fundamental domain, right? So reminder of the definition. So it's this intersection where we have a priori fixed this W, and we take it with the property of not being fixed by any non-identity element of gamma, right? So the only element of gamma that fixes it is the identity, and that since we know that the elliptic fixed points of gamma do not accumulate in the hyperbolic plane, we actually know that that most choices of W work, right? So because the only possible choices of W that are forbidden are precisely the elliptic fixed points of gamma, which don't even accumulate in H. Right? So in a way, somehow it's easy to find such W's, and then this to form this H gamma of W, what we see is that for each non-identity element of gamma, we look at W and at its image under gamma, and well, here is the mediatrix or bisector, right, between W and gamma of W, because it's the set of all Z's that are equidistant to W and gamma of W, right? So somehow, let's say that W is here, and then somehow gamma of W is here. So this would be L gamma of W, and then H gamma of W, at least in this picture that I'm temporarily drawing, would be this half plane, this half hyperbolic plane, and somehow one exercise is that this L gamma of W is actually a shortest curve perpendicular to the shortest curve segment between W and gamma of W. Right? And to solve that problem, it's enough to, you know, like W and gamma of W somehow up to, let's say working in the upper half plane, up to elements of PSL2R, somehow conjugating the whole gamma and sending W and gamma of W, so that somehow they really their images under some element of PSL2R have the same imaginary part and really are, you see, like the real parts are really, one is minus the real part of the other. And once one achieves that, then one can see that this one is precisely the positive part of the imaginary axis, hence a shortest curve perpendicular to the shortest curve that joins W and gamma of W. And then one argues to see that this happens kind of in general, right? So somehow for every W and every gamma of any Fuchsian, which is not the identity, which is a non-identity element of any Fuchsian group. Okay, and then, like for instance, in this picture, where in the case where this one is for instance the positive part of the imaginary axis, and let's say that W is here, then H gamma of W is this part. So that's why I say half plane, right? Half hyperbolic plane. Okay, so that's the Dirichlet polygon. Some properties, right? Well, which I discussed briefly last time. For instance, I discussed why this distance tends to infinity for any enumeration of the elements of gamma. In other words, I mean, for any enumeration of the elements of gamma, this distance goes to infinity. So somehow this one's really go infinitely far away from W. Okay, and then let's just show that the Dirichlet polygon is a locally finite fundamental domain, well, hyperbolically convex. That it is hyperbolically convex follows immediately from the fact that each of these H's, each of these H gamma of W's, H gamma of W is hyperbolically convex, and that can be easily seen, for instance, here when we conjugate gamma by some element of PSL2R in such a way that, as I said before, W and gamma of W sit at the same height and at the same Euclidean distance from the positive part of the imaginary axis. In which case, as I said before, this is H gamma of W. In that situation, it's easy to see that this open H gamma of W is hyperbolically convex. And once you know that, then you know that it's true in general that this one is hyperbolically convex in general. And so we know that all of these are hyperbolically convex. So this one, so the intersection of all of them is hyperbolically convex. So the Dirichlet polygon centered at W is indeed H convex. And now let's show that it's open. So we take any point therein, and any compact disk centered at that point, centered at Z, and we notice the following. So the set of gammas for which Z lies in this line, right? So somehow the point is, here is W, here is gamma of W, and somehow oops. And somehow here is L gamma of W. And Z is somewhere here, and the number of gammas that put it inside this one is finite. Well, because this one is contained in the set of gammas that with the property that this disk that the intersection of this disk centered at Z with that L gamma of W is not empty. So somehow it's obvious that this one is contained in this one, right? Simply because Z is in D, and this one is finite because of this property 9, that for any compact set, the set of gammas that for which this bisector intersects the compact set is finite. So here I'm considering this compact set D. Yeah, so both of them are finite. Right. Now, Z is in the Dirichlet polygon, which means that for Z we always have this strict inequality, right? So Z doesn't belong to any of these L's. So in other words, this A is empty. So this one is empty, and B is finite, right? And now knowing that B is finite, so we're in a situation similar to a situation that we encountered before, because so you see, B, well, it's a set of gammas, right? So it's not the set of line, it's not the set of these bisectors, it's the set of the corresponding gammas. But in any case, when I consider the corresponding bisectors, I know that it's finitely many bisectors that have this property. So somehow, let me draw the disk. Somehow, let's say that, oops. Okay, no, so let me do it the other way around. So let me draw the disk, and the number of gammas for which the corresponding bisector intersects the disk is finite, and somehow, and I know that Z is not in any of the bisectors. So I can shrink the radius so that the corresponding compact disk really doesn't intersect any of this, right? And then once I shrink, then I see that this whole disk is contained in this intersection, because otherwise it would cross one of the bisectors. I mean, if it were, so this I shrink the disk so that this disk doesn't intersect any of the bisectors. So from there, I conclude that this shrunk disk is contained in the Dirichlet polygon, because otherwise there would be some point inside. Which is not in the Dirichlet polygon, and so that point would be either in one of these, in a bisector, or in order to go from Z to there, one would have to cross a bisector, contradicting the fact that I took the compact disk small enough so as to not intersect any bisector. So it's kind of, the reasoning is not hard, but somehow the crucial point is that here I can already start with a finite set of gammas, so that I can shrink the disk, in kind of finitely many times, to say, or let's say that I can shrink the disk and still have a positive radius, right? So that's the point. So somehow this number 9 is really essential for this theorem. Okay, now so we see that this is open. Now, yeah. So let me make some parentheses there. So let me resize. Yeah. So this one is open. It's open and convex in the hyperbolic plane. And now, forget a little bit about the hyperbolic plane, and think about convex sets in Rn, and you see, if one has a convex set, Euclideanly convex open set of Rn, then and it's not trivial, but one can prove that the interior of its topological closure is C itself. And this is not trivial. Okay, but so in particular, in particular, this implies that when one has in the Beltrami-Klein model a convex open subset of the Beltrami-Klein model. So this is let me call it I don't know, K for Klein. Then same thing. The same thing happens in the Beltrami-Klein model. But okay. But then, since the fact that it happens for convex open sets of the Beltrami-Klein model implies that it happens in the other models as well. So for this one, that its topological closure, the interior of its topological closure is itself. In other words, here, what you are seeing here, ignore this. If you just look at this, these two are equal. This interior of the topological closure, and well, this one, I mean, sorry, the interior, this one is just this one, even without this, because this one is convex and open. Okay, so I'm going to use that at some point. Now, this closure is contained in this intersection of all the closures, and for each gamma, of course, this closure is equal to the half plane, to the open half plane union the bisector which bounds it. Right? So of course I have this equal to this. Okay, and so if I take something in the boundary, you see I can see that something in the boundary. Well, it has to be here, right? So it has to be in here. In other words, it has to be in all of these sets, right? But being in the boundary, it does not belong to the Dirichlet polygon, which means that it does not belong to one of the EHs. So if I take a point in the boundary of the Dirichlet polygon, it has to be in all of these, but there is some gamma so that it's not there. So for that gamma, it has to be in the other one. So in other words, the boundary, I can see that it's contained in the union of all of this, of all these bisectors. And here comes something a bit delicate, and somehow this implies that the area is 0, but somehow I think it's delicate because I think one can see it if one works with the Lebesgue integral, but with the Riemann integral, I have to say that I have some problems actually seeing it, because we know that each of these has a hyperbolic area equal to 0, and it's a countable union. Yeah, so somehow here I have to say that one has to be careful. I mean, somehow I always have problems being convinced of this for the Riemann integral. But okay, now I'm going to move on to prove that in between the Dirichlet polygon and its topological closure sits a fundamental set for the action of gamma. So what I'm going to do is, for each orbit, I'm going to pick a point inside the orbit. Well, that I can always do, right? I mean, with the axiom of choice, that I can always do. But also, I'm going to do it in such a way that you see that the point I pick minimizes the distance within the orbit, within that orbit. right? So somehow I have W, and I have I have an arbitrary orbit. So let's see. So I have W. Let me green. I have W, and then I have an arbitrary orbit, which may of course be different from the orbit of W. Right? So let me draw it with some other color. I know that it does not accumulate in the hyperbolic plane, and within that orbit, I pick the closest. I pick the one closest to W. So at least with this picture, if I think Euclideanly, it would be this point. But of course, there could be several at the same distance to W. So I pick one of them. And since it may be that infinitely many orbits have several points at the same distance to W, that's why I say with the axiom of choice. But anyway, so among each orbit, within each orbit, I just pick the closest point. Okay, or a closest point. And then I take the corresponding fundamental set. Right? So this is, of course, a fundamental set because I'm picking exactly one point per orbit. And now I notice that in the Dirichlet polygon, I precisely have this because of the definition of the Dirichlet polygon. Right? So it's the intersection of all of this, and this one is the part that with the property that is the points whose distance to W is smaller than the distance of the corresponding gamma inverse of Z. So something which is in the intersection satisfies this for all gammas. Right? So for all gammas, so something in the intersection has the property that the distance to W is less than the distance of gamma inverse of this to W for all gammas. So it's the shortest among all the, and strictly shorter. So it's the shortest, the closest. So among all the orbit. So at least we know that for each element of each point in the Dirichlet polygon has to coincide with it has to be the one I pick. And so the Dirichlet polygon is contained in F. And now,
sorry.
Yeah.
What is P?
It's P of this orbit, because you see here for the orbit O, I took P sub O. Now for any point, its orbit I always denote it gamma dot Z. So this is an orbit O. So what I'm saying is that the point that the point that here I pick for this orbit has to be precisely Z, because of the argument I gave, right? Because being in the intersection, Z really is closer to W than any point in its orbit, and strictly, right? So, okay. Now, so I know this inclusion. And now I want to show the inclusion that F is contained in the topological closure of d gamma W in the hyperbolic plane. So I take any point here corresponding to an orbit O, And then I consider this shortest curve segment, this closed open shortest curve segment, right? So so this is in F, so it would be like this point, and here I'm considering like this hyperbolic shortest curve, but closed here, open here. That's what I'm considering here. And what I'm saying is that if this segment, this closed open segment meets a bisector, so if it meets some bisector, let's say, I don't know, something like this, right? So that this one meets the bisector. Then what happens? Then well, of course, the meeting point cannot be W, of course. So and this has to be O. Sorry, not theta. Yeah, so it has to be the meeting point has to be a point strictly between W and PO, which is what I'm saying here. And then the distance from W to PO is so let me see. So right. So you see the point is that then this PO somehow would be on the other side. That's the point. So here is H, here it would be H gamma of W, and PO would live on the other side, which means that it satisfies the other inequality, right? I mean, it doesn't satisfy this inequality, it satisfies the other inequality because it's completely on the other side. So here it would be for PO, and here PO. And so that's why I write here that the distance from W to PO is then this strictly greater than this other distance. And this distance is, of course, equal to this one. But, yeah, sorry? Yeah, yeah, sorry. Yeah, but then you see, then this would be a point in the orbit, in the same orbit O, whose distance to W is strictly smaller than this one, but PO was supposed to be the one in O closest to W. So that contradicts with this contradicts the choice of PO, and the contradiction comes from the assumption that this one, crosses one of these bisectors. So what must happen? It must happen that this one doesn't cross any bisector whatsoever. But if it doesn't cross any bisector whatsoever, that means that it never leaves the Dirichlet polygon. Because to leave the Dirichlet polygon, you see, the Dirichlet polygon being this intersection, to leave it, you have to leave one of these. That is, you have to cross one of the bisectors. And we are just seeing that precisely you never cross one of them. So this means that so that this one is completely there, but you see then PO can be approximated by points here in this segment, which are all here, so it's in the closure. Right? I mean, here you have a whole segment that tends to it. Right? And so, but PO was arbitrary in F, so F is completely contained in the closure. And so what we have so far is that this one is a hyperbolically convex fundamental domain, because in between D and its topological closure sits this fundamental set, and here, up to certain, up to really thinking a bit carefully about the area of this union, the hyperbolic area of this union, the boundary has a hyperbolic area equal to 0. Now, part of the theorem, part of the statement of the theorem is this, that it's locally finite. So that's the final part. And what I'm going to do is I'm going to show that d gamma of W satisfies the condition of local finiteness with respect to compact disks, not with respect to arbitrary compact sets, only with respect to compact disks. And it's going to be an exercise for you to prove that this is enough. Okay, I mean, it's actually going to be a hand-in exercise. Okay, so take a compact disk of radius, of positive radius, centered at W. Yeah, so it's going to be, okay, compact disks centered at W. Yeah, so sorry, so okay. So in the exercise, I have to you have to assume this centered at W. Anyway, and then consider any gamma with the property that this intersection is not empty. Okay, and take a point in such intersection. Then what we have is that I take the distance between W and gamma of W for this gamma that I'm considering, and I put Z in between, and then I use the triangle inequality. So this distance is less or equal than the distance from W to Z plus the distance to Z to gamma of W. This one is less or equal than R, because Z is in this compact disk of radius R centered at W. Yeah, plus, yeah, so this one is less or equal than R, and then this one, I think I have to, right, so because so I want to use that to see that this is less or equal than this. Right. I mean, so Z is here. Right. So Z is of the form gamma of something that lives in this closure. So gamma of something that here satisfies these inequalities, but not the strict inequalities. Right. And so so it's gamma of something satisfying this. And here,
the smaller equivalence for the first part of the, if you go back to the actual thing.
Yeah.
Smaller or equal is for omega for W to Z, because Z we picked in the compact disk with radius R.
Mm-hmm.
So if it's in this disk centered at W, it has to be a distance smaller or equal to R, because that's the radius of the compact disk.
Mm-hmm.
So that's a smaller or equal.
Mm-hmm.
And the other one is actually.
Or did I make a mistake and should it be Z? Yeah, I mean, because I think that's what you were going to say, right? I mean, if here I write Z, then I agree. Yeah, then this is just equal to this, right? And then this little equal than smaller or equal than this. Yeah. Okay. So let's see, because maybe it was a mistake, and then that.
Distance is the same because you apply.
Yeah, this one is because to this one you apply gamma inverse, and it's an isometry. So this would be the same as this one. And now I only need to see that this one is smaller or equal than this one. Right, so Z is here. Right, Z is here, right? So gamma inverse of Z is here without the gamma. And so it's I want to say that then it's smaller, that the distance is smaller or equal than anything in the orbit, in particular for Z. Right. Yeah, was that clear? Yeah. Okay. Yeah. So okay. So indeed was here as Z. Okay, and then right, and so this is smaller or equal than this, and then again this one is smaller or equal than R. Okay, so for this Z, what I obtain is that this distance is less or equal than 2R. Right. So you see, what I obtain is that for that the gamma I consider with the property that this intersection be non-empty necessarily satisfies that this point in the orbit of W is in the disk centered at W with radius at most 2R, right? So gamma of W, that's strange. Okay, but, is in the disk in the disk centered at W of radius 2R. Let's say 3R because it's less or equal. Right, but only finitely many gammas in gamma can satisfy this because the orbit doesn't accumulate anywhere. Yes? No.
Because there's no fixed point.
Well, yeah, W is not a fixed point, right? Yeah. Yeah, and so only finitely many images can live here because its orbit doesn't accumulate anywhere, in particular in W itself. Okay, so only finitely many gammas have the property of making this intersection non-empty, because for any of them, I can yeah, I mean, I can see that I am getting stuck. Sorry. I mean, because R is fixed. Okay, so what we have shown is that for any compact disk of positive radius, centered at W, the number of gammas for which the intersection is not empty is finite. And then the exercise is that to show that this suffices in order to deduce that it's locally finite, right? Which is what I ask you to as hand-in exercise. But so here it's that every compact disk, and then here what we have shown is not any compact disk, but is centered at W. Yeah. So what should be the idea? That if you give me any compact set in H, it's contained in some compact disk around with center W, and that's it, right? I mean, okay, so it's solved. Okay, and so this one is indeed a locally finite fundamental domain. No, I mean, I think this would be more clear. Take a geodesic, a shortest curve like this. You see, like, consider some triangle like this. Right? I mean, it's this one together with this one. Right? Its area is pi minus 0 minus this one, right? So it's pi minus this angle, I don't know, alpha. Oops. Minus alpha. And now let somehow this point tend to the line.
Ah, right. And then
yeah,
they cancel each other.
Somehow, and then yeah,
resulting area would be exactly that of the geodesic.
Right.
Right.
Yeah.
Okay.
It's not a formal argument, right? But somehow.
Yeah, I'm happy with that.
Yeah. Okay. I mean, if you want, you can say okay, and then you see kind of to trap everything, right? Kind of, because somehow here it's not trapped. The shortest curve is not trapped, but then maybe you can say trap it, right? So.
Right. Okay.
Right. And then maybe and then just let the 2 points tend. Right. I mean, yeah. I don't think it counts as a formal argument, but at least it's, yeah. And then I wonder whether one can do the same for this one. Maybe. Trap all of them.
Yeah.
In a bunch of squares, all of whose areas you can make as small as you want. Maybe. Okay.
Then we wouldn't even have the problem that we have to consider the back integrals, right?
Right.
That was just using the formula we already proved.
Yeah, I think so. Yeah. Okay.
Yeah, thank you.
Yeah. And okay, and then a Dirichlet polygon for PSL to Z that we started discussing last time. So somehow we consider three elements of PSL to Z, namely translation by 1 to the right, gamma inverse, which is then translation by -1, I mean by 1 to the left, and this one, which is somehow around the point I, is the 180-degree rotation. So the elliptic of order 2, fixing I. and we draw those three, the three bisectors, namely this one for the elliptic of order 2 with fixed point I, and so for this one the corresponding H is this whole thing. This one for translation to the right. Yes, sorry, and I haven't said that I mean it's written, but I haven't said it. That as a center of the polygon, I'm taking anything here in the imaginary axis strictly above I. So anything here. So let's say here. So you see translation by 1 to the right is here. Bisector is this one, and the corresponding H is this thing. Right? And same thing for translation by 1 to the left. Translation by 1 to the left. By 1 to the left. Bisector, and then the corresponding H is all of this. And so the intersection of the three H's is the P that you are seeing there. Right? And of course, it goes to infinity. So you see somehow P really is a triangle, right? I mean, because these two go and join at the point at infinity. So it's actually this triangle with this kind of extra distinguished vertex, because it's a fixed point of an element of gamma, or an element of PSL2Z. Yeah, and the claim is that this P is the Dirichlet polygon for that arbitrary point above I. Okay, so P is the intersection of three H's, and the Dirichlet polygon is the intersection of all H's. So the Dirichlet polygon is contained in P. Okay, so and now to prove equality, well, let's suppose that it's not equal, so that it's properly contained. Then the first claim was that there are 2 points in this P that are gamma congruent. Right? So that there is a point whose image is also there for some element, so for some non-identity element of PSL2Z. Now, I'm assuming this, so I know that there is a point in P, not here. So there's some point. Yeah. So there's. Copy. Right. So there's a point in P, not in D. So let's say that D is somewhere there. So there's a point P not there. Right. And now I know that since P is open, because I'm taking it the open polygon, right? So kind of excluding the boundary. And so I'm and here I'm assuming this proper inclusion of open sets. Right? But the point is then that I know that there is someone in P, not in D, and yeah, what I want to claim, I mean, what I know is that for this one, there is some element of PSL2Z that puts it inside inside D bar. I mean the topological closure. Not so what, right? Let me think. Yeah, okay, so I want to produce 2 points in P that are gamma congruent, 2 different points that are gamma congruent, just from the assumption that D is properly contained in P.
P is open, right?
P is open, yes. So
Take some closed set inside it, and there will always be a copy.
no, say it again.
This blue thing is
Yeah.
D.
D, which is also open.
I see.
If D isn't equal to P, then we have some gamma for which H gamma is smaller than P. So we also have the other side of this H gamma, the other half, in which this point would lie, maybe.
Right. So let's say,
You'd be able to find another L which somehow goes through P, cuts through P,
right.
and yeah. No?
No, yeah, sure. The point is, then somehow we would like to show that such thing is impossible, right? But that there is no other L gamma, any bisector, that crosses P. But somehow that seems to be equally hard, right?
But we know that the elements we've chosen generate the group, right?
I don't know if we already know it. We haven't shown it.
Okay, but
Yeah,
it's true. Right?
it is true, but yeah, but we haven't shown it.
But maybe you can use that and then see that it's impossible to have a complement of D inside of P.
Yeah, so let's see. For this one, let's see. For this one, I know that there is some disk around it contained in P. Right? For this point, in P, not in D. Now, this point in P, not in D, is gamma congruent to some point in the topological closure of D, because we already know that D is a fundamental domain. So so it's equivalent to something in D bar. Okay. Right, and then I look at the image of this one under the element of gamma that of PSL2Z that gives me the congruence. So the image is a disk of the same radius and now centered here. Right, and now this one is in the topological closure of D. So this disk intersects D. So there is some point in D lying inside the disk, which is the image of this disk. So there is a point in this disk, gamma congruent to a point in this disk. And then you can say yes, and those 2 points may be the same point, in which case you haven't reached a contradiction. This could be an elliptic fixed point a priori. Okay, but elliptic fixed points do not accumulate. So there is some other point in this disk that goes still inside that disk, and it's not an elliptic fixed point, and so they are indeed different. And then you have two different points in P that are gamma congruent. Yes?
Why is that a contradiction?
No. It's just yeah, you're right. I mean, it's just that from this I want to extract two distinct points that are gamma congruent. Yeah. Okay. Oof. Okay. And now such a matrix indeed exists, and then the exercise is that in this matrix none of these two are zero. Right? For instance, if C is zero, A can be put as a composition of an integral translation with an integral homotopy, and then one can see that it has to be completely taken out. That this Z is taken out if Z is zero, right? And something similar if D is zero. Okay, so are we together or are we okay or not? Or do you want me to go back?
I see that when C is zero, it is a translation.
No, but and then with the existence of two different points that are gamma congruent, do you agree? Kind of with this argument that I gave of, like that there is some point here which is gamma congruent to a point here, and those two are actually different points. That I can take them as different points. Do you agree with that? Yes? Okay. Okay. Now, yeah, okay. Now, the exercise is both of these are not zero, and then somehow I'm just saying that, for example, if C would be zero, if C were zero, then one could write this as a composition of a translation and an integral translation and an integral homotopy.
But there is no integral homotopy.
No, I would say there is, for instance.
In SL2Z. C is zero, then the diagonal edges have to be ones.
Right, you're right, because you're right. Yeah.
It's just a translation.
Yeah. But and then the point is that Z has to be completely taken out, right? In contradiction with, and somehow the idea is that if one assumes that D is zero, then one reaches a similar conclusion. Okay, now I'm taking this z in P, so in other words, it's between minus 1/2 and 1/2. And then I did, yeah, sorry, this is, yeah, sorry. So it's between minus 1/2 and 1/2. And so I just multiply by 2. So 2 times this is between minus 1 and 1, of course. And then I multiply with CD. And then you see, and then I have this inequality regardless of whether CD is positive or negative. Right? And it's just because I here have minus 1 less and this less than 1. So I can play around so that I indeed have this inequality. Right? I mean, if let's say if CD is positive, then I just multiply with CD and then use this one. And if CD is negative, I use the other one and the reversal of the inequality. So in any case, I always have this. And so, well, I compute this norm square. Well, I just substitute for z. Yeah, and then compute the norm square. So this is not a big deal. Expand this square, and then here realize that here is 2x. I mean, x is the real part. Yeah, and then here I have, you see, I have this d square here, this one here, and then the rest is c square times the norm square of z, right? Because it's x squared plus y squared. Okay. And this is greater or equal than, and then here it should be, oops. Here it should be, you see, the norm square of z is greater than 1 because z is in P. Right? So it's greater than 1. So this one is greater than 1. And this one is greater than minus absolute value of CD. Okay. And this one, then I collect, and you see this is equal to this plus this, right? I mean, if I expand this square, I get this square, and then minus 2 times this, and then minus 2. But so I cancel one of them. So just to have just one of to have just minus 1 here. Okay. And this is the point is that this is a positive integer. Right? I mean, positive. I mean, non-negative, but yeah, and CD, and this, and none of this is 0. So this is actually positive, and so it's a positive integer, so it's at least 1. So what I obtain is that this is at least 1. Right? And then when I compute the imaginary part of mu a of z, well, we had already computed it. And what I obtain is that then because this is greater than 1, what I obtain is that this is less than the imaginary part of z. No, because here you have greater, right? So you have this is greater than this positive. So it's kind of, this is at least 2, right? Yeah. Okay, and now I start. I see. You see now this one is in P. Right. Yeah, there is just something. Yeah, there is something. I mean, you see somehow what I want now is kind of, you see, to start applying mu a, and start getting imaginary parts smaller and smaller. But something that I notice is that how do I know that mu of this is again in P? That's yeah.
If you go back to what you drew, at some point the imaginary part would be too small, I guess.
Can you say it again?
Like P is cut off at some point. You can't be smaller than
Right.
this minus 1/2 plus 1 square root of 3/2. That's like the lowest the imaginary part can get to still be in P.
Right. Yes.
Oh, sorry.
No. Yeah. No. I mean, yeah. No. Exactly. No. I mean, what I want is precisely then to see that I accumulate somewhere. But for that, you see, for that I need for somehow. I mean, somehow you are right that somehow what I want is to see that the imaginary part has to be smaller and smaller and smaller, but it has to be positive, so there has to be some accumulation point, kind of in contradiction to the discreteness. But for that, I need to guarantee that I always land in P. But somehow I'm not guaranteeing that, right? I mean, I know that this one is in P, and I'm saying that a sequence of elements of P, but how do I know that each one of them is in P? Yeah, and as you say, this is not correct, because this here I would have to put here what you said, this one instead of 1. Yeah, let me write that, but it still doesn't solve my problem. So yeah, so square root of 3/2, but it still doesn't solve my problem. How about this? Now forget about this sequence, because I cannot. You see the problem, right? That I cannot guarantee that mu a of that is in P. But forget about that. And you see the point is that I had 2 points in P related by this mu a. And what I saw is that the imaginary part of one has to be strictly smaller than the imaginary part of the other. But now play the same game with the inverse, and then you are going to arrive at the imaginary part of this one that must be strictly smaller than the imaginary part of the other one. And then you have two strict inequalities, and that's impossible. Yeah, do you agree or not? I mean, here you see somehow, I mean, I took two points in P that are gamma congruent. Then they are gamma congruent, so I take a matrix so that it sends one to the other. And what I get is that one of the points has imaginary parts strictly less than the other. But now apply the same argument, let's say to mu a inverse, blah blah blah. and you arrive at this corresponding conclusion, but for A inverse, and this is then this imaginary part is strictly smaller than this imaginary part. You just use the same argument, but for A inverse.
But we're not claiming that A of Z is the same as A inverse of Z.
No.
Did they make some assumption?
There was no. Yeah, I mean the only thing it was that it's an SL2Z. I mean that you have to show that C and D are not zero. But if you show it for this one, then for A inverse, you see now you think this is your new Z and this is your mu A inverse of Z.
Yeah.
And then you apply the same. And the contradiction is that then you obtain two strict inequalities, right, between two real numbers.
But you have Z, which has larger imaginary part
Than this one,
Z.
yeah, and then you would arrive at this one strictly less than the imaginary part of Z. And that's the contradiction.
How can you use that?
I mean, by applying the same reasoning, but with mu A of Z and Z reversed.
Okay.
And not for A, but for the matrix A inverse, which is the one that takes this one, that reverses the role. So what I'm saying is, from these 2 points, you see 2 points that are 2 points in P that are gamma congruent, and what you arrive is that however you arrive is that one of them has imaginary part strictly less than the other one. And then you say, okay, now reverse the role and use the same reasoning, and you arrive at the other strict inequality.
Could you actually write it down, the other inequality?
Yeah, so the other inequality would be for let's say I would arrive at imaginary, let's say, of mu A of Z greater than something in between equal to imaginary part, and then here I would actually say, let's say, mu A inverse or mu A inverse mu A of Z, and this is yeah, imaginary part of Z. And the point is, that's impossible, right? I mean, you cannot have this strictly less and this strictly less.
But when you apply it for mu A inverse, then C and D won't be
Those are some other numbers to which you can apply kind of the same skeleton.
Okay.
Somehow it's not that you're going to have the same C and D and the same Z, but kind of the skeleton is going to be the same. So somehow the reasoning is, if this inclusion is proper, then you have two points in P that are gamma congruent, and for them you can prove both this and this, and that's impossible. So what must happen is that here you actually had equality. Yeah, so that's the reasoning. And somehow, first, my mistake when preparing was that somehow I didn't realize that I couldn't prove that mu A, that I could guarantee that mu A was always in P. So somehow, like, kind of what I wrote here is really, I cannot guarantee that. But it's not necessary because what I say is, okay, this argument is symmetric, so I can reverse the roles and obtain a contradiction. Okay, sorry about that. Whew. Okay, So somehow I overcomplicated it somehow. But anyway, now there is something. I mean, but now we agree, right? Okay. Now there is something which is that of course there can be different fundamental domains. And actually, I would say, like for instance here, I mean here I would say it's kind of clear that you see, like from this that I already know is a fundamental domain. What I decide to do is like cut off this stripe, and then say okay, and then replace it, right? And then somehow, at least intuitively, it's clear that what I obtain is another fundamental domain. And somehow the challenge would be to see if this actually coincides with the Dirichlet polygon of some point here, which is no longer above I, but kind of slightly moved to the right. Right. Yeah, and then this one, which I mean, okay, this hand in, which I think I pretty much solved, right? Yes. Yeah. Okay. Anyway, sorry, I tend to do that. Okay. Okay, so I will stop it here.